So it's my great pleasure to introduce Ellen Vitercik. Ellen is a graduating student at CMU. She will be defending in a month, right, or later this month. So I'm sure it's going to be an excellent defense. And soon she will start a postdoctoral her postdoctoral position at UC Berkeley. And after that, she will move on to Stanford, where she will start her faculty position. Take it away, Ellen.
Thank you. So I'm going to be presenting a paper called How Much Data is Sufficient to Learn High-Performing Algorithms. And this is joint work with Nina Balcan, DeBlasio, Travis Dick, Carl Kingsford, and Tuomas Sandholm, and it appeared this year in Stock. And it's something that Tuomas mentioned briefly in his talk, but I won't assume that you've seen that talk. So algorithms often come with a ton of tunable parameters, and these parameters can have a significant impact on the algorithm's runtime, its solution quality, and so on. Oftentimes, domain experts are left to tune these parameters by hand, which is just a notoriously time-consuming, tedious, and error-prone process. So for many of those algorithms that are typically used in practice, no configuration of these parameters admits a meaningful worst-case guarantee. So these parameters are made available for the user to tune. So this is true, for example, of the integer programming solvers that Tuomas was talking about in his talk, which come with a ton of tunable parameters. And with a deft configuration of these parameters, they can be used to solve very computationally challenging problems. Alternatively, as is often the case in theoretical computer science, these parameters are tuned implicitly within the proof of a worst-case guarantee. But these worst-case instances may be rare or non-existent in practice. So our goal in data-driven algorithm design is to automate this process of algorithm configuration or parameter tuning with the help of machine learning. So at a high level, and I'll be much more detailed about this later in the talk, but at a high level, the input to this automated configuration procedure is a training set of typical problem instances from our specific application domain at hand. And this training set is assumed to be sampled from some unknown application-specific distribution. So in the example of integer programming, this training set could be a set of all of the routing integer programs a shipping company had to solve over the course of a year. And we're assuming that those integer programs are sampled from some unknown application-specific distribution. The output of our automated configuration procedure is a configuration of those parameters, which has strong average empirical performance over our training set. And by performance, I mean, for example, runtime, solution quality, and so on. So whatever parameter setting we come up with this automated procedure, it should ideally also have good performance on future problem instances from the same application domain, but which aren't already in our training set. In this paper, our main contributions are a broadly applicable theory for deriving generalization bounds for a data-driven algorithm design. And these bounds tell you, for any choice of my algorithm's parameters, what's the difference between the algorithm's average empirical performance over the training set and its expected or future performance on problems from our unknown application-specific distribution? So if this difference is indeed small, then we can be guaranteed that average performance over the training set will be indicative of future performance for any parameter setting we come up with, which means that these results apply no matter how you tune your parameters via an optimal or suboptimal approach, a manual or automated approach. Prior research has proved these types of generalization guarantees by giving case-by-case analyses, looking at clustering algorithm configuration problems, integer programming configuration, different types of selling mechanism configuration, and greedy algorithm configuration. In this paper, we uncover unifying structure, linking these seemingly disparate configuration problems, which allows us to provide very general guarantees that apply to all of these problems simultaneously. But despite the generality of these guarantees, we're still able to recover the bounds from prior research and prove novel bounds for configuration problems that hadn't been studied already in this light, for computational biology algorithm configuration and voting mechanism configuration. So what does this unifying structure look like? Well, at a high level, our guarantees apply to any parameterized algorithm where at a high level, its performance is a piecewise structured function of these tunable parameters. So to give a picture, you could imagine that we're tuning two parameters, rho 1 and rho 2, along the x and the y axis. And we're measuring here the algorithm's performance, so its runtime or its solution quality, on some fixed input as a function of these parameters. And in this picture, it's a piecewise constant function, but it could also be piecewise linear or piecewise something else. So let me take a moment to point out what are the key challenges we face in trying to provide these provable guarantees for algorithm configuration. And it's really that in these combinatorial domains, an algorithm's performance is just a notoriously volatile function of these parameters. So for example, in this picture, you could imagine we're tuning one of these parameters rho along the horizontal axis, and we're measuring the algorithm's performance, so its runtime or its solution quality, as a function of this parameter. It's just a very volatile function with many jump discontinuities. And intuitively, this is because in these combinatorial domains, if you just tweak the algorithm's parameters by a little bit, you can cause a cascade of changes in the algorithm's behavior, which causes these jumps in the algorithm's performance. So overall, there's just a very complex connection between an algorithm's parameters and its performance on any given input. Meanwhile, for those functions that we really understand well from a theoretical perspective in machine learning, there's typically a fairly straightforward connection between a function's parameters and its value on any given input. And since we don't have this predictable structure in combinatorial algorithm configuration, we have to understand what structure is there which will allow us to provide these types of provable guarantees. And in this paper, we look at this piecewise structure, which we see in so many different domains. So to ground the rest of this talk in a running example, I'm going to tell you about a configuration problem from sequence alignment. So the input to a sequence alignment algorithm is a pair of sequences like these two here. And the output is an alignment of these sequences. There are a lot of different features that we might care about in an alignment, such as the number of matches, the number of mismatches, the number of indels or insertions and deletions, indels for short, where I've matched a sequence character up with a gap character, and the number of affine gaps, which are these consecutive sequences of gap characters. So a standard algorithm for sequence alignment is defined by three tunable parameters, rho 1, rho 2, and rho 3. And it uses dynamic programming to return an alignment which maximizes this parameterized objective function, which is the number of matches minus rho 1 times the number of mismatches minus rho 2 times the number of indels minus rho 3 times the number of gaps. Sometimes in sequence alignment, we can access a ground truth reference alignment of these sequences. So this is true, for example, sometimes in computational biology. But this requires extensive manual alignments by a domain expert. So we'd rather just run the parameterized algorithm from the previous slide. But this raises a question, how do we tune that algorithm's parameters? As Gusfield wrote, there's considerable disagreement among molecular biologists about the correct choice of the parameters. Ideally, we'd like to somehow be able to guarantee that using our parameterized algorithm, we're able to find an alignment of these sequences that is close to the unknown ground truth alignment of the sequences. And to illustrate the power of a well-tuned algorithm, here's a ground truth on alignment of a pair of protein sequences. And here's an alignment by an algorithm with poorly tuned parameters. So the blue regions here indicate where the algorithm's output matches up with the ground truth alignment. Meanwhile, here's an alignment by an algorithm with well-tuned parameters. So you can see that the algorithm with well-tuned parameters is able to recover much more of the ground truth alignment than the algorithm with the poorly tuned parameters. So what would this automated parameter tuning procedure or automated algorithm configuration procedure look like for sequence alignment? Well, first we would fix some parameterized algorithm like the parameterized algorithm from 2 slides ago. Then we would receive a training set of typical problem instances from our specific application domain. So in the case of sequence alignment, each element of our training set would be a pair of sequences together with a ground truth alignment of those sequences, aligned by some domain expert. Then we perform some optimizations and we'd find a parameter setting which has good average empirical performance over our training set. So in general, this can mean good average runtime or solution quality. And in this sequence alignment example, it would mean that on average over our training set, that alignment output by our algorithm is close to the ground truth reference alignment. And the key question we want to answer, which again is the focus of this talk, is will that parameter setting also have good future expected performance on our application-specific distribution? So on a new pair of sequences where we don't even know what the reference alignment is, can we guarantee that the algorithm's output will be close to that unknown ground truth alignment? Okay, so now with this example in mind, I'm going to tell you more about our model and problem formulation. And we're adopting this learning theoretic model of algorithm configuration introduced by Gupta and Refgarden in an ITCS 16 paper. So RD is going to be the set of all parameters, and X is going to be the set of all inputs to our algorithm. So for example, this could be a set of sequence pairs. So one element of the set X would be a pair of sequences. A little more formally, what do I mean by algorithmic performance? Well, I'm going to use the notation U row of X to denote the utility of the algorithm parameterized by row on the input X. So I'll use the terms algorithmic performance and utility somewhat interchangeably. And again, for example, this could be a measure of runtime, solution quality, distance to some ground truth solution, and so on. For notational simplicity, I'm going to assume that U row of X is bounded in the interval -1, 1, but this can easily be generalized to any bounded interval. We're going to make a standard assumption, which has been made for decades in this literature on automated algorithm configuration, which is that there's some unknown application-specific distribution D over inputs to our algorithm. And this is supposed to model our specific application domain at hand. So for example, in the context of sequence alignment, this could be a distribution over pairs of DNA strands, or a distribution over pairs of protein sequences that a biolab has to align on a day-to-day basis. So now using this notation, I'm going to describe the key question we want to answer a bit more formally. We want to know for any choice of our parameter setting row, is that parameter setting's average empirical utility over the training set close to its expected utility on our unknown distribution. So mathematically, given sample problem instances x1 up through xn from our application-specific distribution, we want to know for any choice of our parameter setting, what's the difference between its average empirical utility over our training set and its expected utility on our unknown distribution. And if this difference is indeed small for any choice of our parameters, we can be guaranteed that strong average empirical utility will it be indicative of strong expected utility. And here, expected utility is really a proxy for future utility on future problems from the same application, but which aren't already in our training set. I think there might have been a question. Oh,
no, I think that, so I don't see a question.
okay.
I think it was me messing up with the Q&A. So
okay.
Sorry for the distraction.
No problem. Okay, so I mentioned at the beginning of the talk that our guarantees apply when the algorithm's performance or its utility is a piecewise structured function of these tunable parameters. So let me give an example of one such function, again, in the context of sequence alignment. So let's remember that sequence alignment algorithm from two sections ago. We want to find an alignment which maximizes this parameterized objective function defined by these three tunable parameters, row 1, row 2, and row 3. So I'm going to rely on a key lemma, which was proved over 2 decades ago by Gusfield et al. In a pretty different context. So Gusfield et al. Proved that for any pair of sequences, like this pair here, there's a small partition of the parameter space, R3, those 3 tunable parameters. So there are 3 tunable parameters in this picture. I'm just illustrating 2 for the sake of the illustration. But there are 3 tunable parameters. There's a small partition of this parameter space such that in any region, like this blue region here, the algorithm's output is fixed across all parameter settings in that region. So what I'm saying is that if I was to use any parameter setting from this blue region, I would, for example, always get this particular alignment. And if I looked at another region of this partition, no matter what parameter setting I use in this other blue region, I would always get this particular alignment. And so an immediate corollary of this lemma is that the algorithm's utility, so the distance between the algorithm's output and some ground truth alignment, is a piecewise constant function of these tunable parameters, using the exact same partition as from the previous slide. Okay, so now with this example of a piecewise structured utility function in mind, I'll tell you about these piecewise structured functions a bit more formally. And to do so, I'm going to tell you a bit about this concept of a dual class. So let's remember this notation that I had introduced a few slides ago. U row of X, the utility of the algorithm parameterized by row on the input X. So if I collect the set of all such functions U row, I'll denote it U, and I'll refer to it as the primal function class. And in learning theory, typically we prove these types of generalization guarantees by understanding the intrinsic complexity of this primal class U. And by intrinsic complexity, I mean, for example, its VC dimension, pseudo dimension, Rademacher complexity, and so on. But the challenge in these algorithm configuration scenarios is that this primal function class U is pretty gnarly. So for example, in sequence alignment, every element of the domain of these functions in the set X is a pair of sequences. So it's unclear how to plot or even visualize these functions U row. And there's certainly no obvious notions of Lipschitz continuity or smoothness that we could rely on to bound the intrinsic complexity of this primal function class U. So this is where this notion of a dual function comes in handy. So rather than fix the parameter setting rho and vary the input x, I could just as well fix the input x and vary the parameter setting rho. And I'd get the algorithm's utility as a function of its parameters. And as you would hope, ux of rho equals u rho of x. And if I collect the set of all such functions ux, I'll denote it u star, and I'll refer to it as the dual function class. And the dual functions are nice because they have this simple Euclidean domain, Rd, the set of all parameters, and they often have ample structure we can use to bound the intrinsic complexity of the class that we actually care about, u, the primal function class. So what I've been alluding to throughout this talk is that across all of these different domains, these dual functions, utility as a function of the parameters on some fixed input, is piecewise structured. It's piecewise constant, piecewise linear, or piecewise something else. So to give another example besides sequence alignment, in a Cold 17 paper, we looked at different parameterized clustering algorithms. And these parameters allowed you to interpolate between several classic clustering algorithms like complete, single, and average linkage. And we proved that for a wide variety of quality metrics for clustering, such as the k-means objective value, these metrics are piecewise constant functions of these tunable parameters. So the dual function is piecewise structured on a fixed clustering instance. These clustering quality metrics are piecewise constant. Okay, so now with this piecewise structure, I'm going to tell you about our main result. And first, I'll tell you a little bit more about this notion of intrinsic complexity from learning theory. So the intrinsic complexity, CG, a real value of a function class G. At a high level, these notions of intrinsic complexity from learning theory are meant to measure how well functions in this class G are able to fit complex patterns. So for example, these sine functions on the left would have a higher intrinsic complexity than these constant functions because the sine functions are able to fit more complex patterns. And there are a lot of different specific ways we use to quantify intrinsic complexity in learning theory, such as BC dimension and pseudo dimension. Okay, so with this notion of intrinsic complexity, I'll give you the flavor of our main result, and I'll start off with a picture. So in this picture, let's say that we're varying two parameters, rho 1 and rho 2. There can be any number of parameters, but in this picture, let's say that there are two. And we're plotting an algorithm's dual function. So fix the input x and look at the algorithm's utility as a function of these parameters. And again, this can be a measure of the algorithm's runtime, solution quality, memory usage, and so on. Okay, so let's say that for any input x, there are these functions g from some set g, which partition the parameter space into regions. So in this picture, there are three functions partitioning the parameter space into 1, 2, 3, 4, 5, 6 regions, such that in any region, the dual function, algorithm's performance as a function of the parameters, is equal to some function f from some set f. So in this picture, f would be the set of all constant functions, but it could be any set of functions. So let's say that the structure holds for any input x. We prove that with high probability for any choice of the algorithm's parameters, the difference between its average empirical utility over the training set and its expected utility over our unknown distribution is bounded by the square root of CF plus CG, where I'll be more specific on about this on the next slide, but at a high level, CF is the intrinsic complexity of the set F of piece functions, and CG is the intrinsic complexity of the set G of boundary functions, times log K, where K is the number of boundary functions, divided by N, where N is the size of our training set. So for those of you familiar with learning theory, specifically what we prove is that the pseudodimension of the U, the primal function class, algorithm's utility as a function of the input, is bounded by the pseudodimension of the dual of the set of piece functions plus the VC dimension of the dual of the set of boundary functions times log K, where K is the number of boundary functions defining each of these piecewise partitions. So to give you a brief idea of how we prove this theorem, I'm going to tell you about a key lemma that we use. So you can think of each of these boundary functions defining this piecewise partition as a binary function, which splits the parameter space into two regions. So imagine we've got row 1 along the horizontal axis, row 2 along the vertical axis, and this boundary function splits the parameter space into two regions, one where the parameters are labeled -1, the other where the parameters are labeled +1. But we don't just have one boundary function. For every problem instance, we have K boundary functions. So we want to know, given K boundary functions, how many sign patterns do they make? So in this picture, we have K equals 3. And they make 1, 2, 3, 4, 5, 6, 7 sign patterns. So just written mathematically, say you fix these K boundary functions if you want to know, as I vary the parameters, how many sign patterns do I get? And these are binary functions. So many of you may be familiar with this classic lemma from learning theory, Sar's lemma, which tells us that for any K points, in our K parameter settings, row 1 up through row K, if we fix those K parameter settings and vary the boundary function G in the set G, how many sign patterns do we get? And that's bounded by E times K, the number of points, to the VC dimension of the set of all boundary functions G. But this doesn't quite answer the question we want to know, because here we're fixing the K boundary functions and varying the parameter setting, whereas here we're fixing the K parameter settings and varying the boundary function. So this is where transitioning to the dual functions comes in handy. Because it turns out by transitioning to the dual functions, we can bound the number of sign patterns we get by varying the parameter setting and fixing the K boundary functions by E times K. K is the number of boundary functions to the VC dimension of the dual of the set of boundary functions. So hopefully this just gives you an idea of why transitioning to the boundary functions helps us to understand these piecewise partitions of the parameter space and why we see the dual functions showing up in so many places in our main theorem. So now I'm going to give an application of our main theorem, again, to this running example of sequence alignment. So let's remember that structure we saw a few sections ago. We saw that if you fix the pair of sequences S and S prime, the algorithm's utility, so the distance to some ground truth alignment, is a piecewise constant function of these tunable parameters. And if we just plug in what we know about this function to our main theorem, we get that with high probability for any choice of our parameter setting, the difference between the algorithm's average empirical utility over the training set and its expected future utility is bounded by the square root of log the maximum length of these sequences divided by n, where n is the size of our training set. So the takeaway is that so long as this difference between average empirical utility and expected utility goes to 0 pretty quickly as the number of training examples grows. So now I'll just wrap up with some conclusions and future directions. So in this talk, I described this unifying structure, this piecewise structure, which connects these seemingly disparate configuration problems from clustering, integer programming, selling mechanism configuration, greedy algorithm configuration comp bio, and voting mechanism configuration. And we use this structure to provide extremely general generalization guarantees. So to a few directions for future research, this talk, we really focused on generalization guarantees for algorithm configuration, and they were uniform convergence in the sense that they held for any parameter setting you come up with, which means that you can apply them to any configuration procedure you might use to optimize your parameter setting, an optimal or suboptimal procedure, a manual or automated approach. But a very natural question is, how can we quickly find provably good parameter settings? There are a lot of heuristic approaches we might take, but how can we provably find good parameter settings? And there's a growing body of research on this more theoretical question, but still many open questions. I think in this paper, we really kind of got to the bottom of how this piecewise structure that we see in so many different areas allows us to provide generalization bounds, but how can we also leverage this piecewise structure to get fast, provably good parameter optimization algorithms. Another direction, in this talk, we focused on learning one parameter setting that's good in expectation on our unknown application-specific distribution. But a more flexible approach would be to learn a mapping from problem instances to parameter settings. So in this picture, you can imagine we're varying two parameter settings, row 1 and row 2 along the horizontal and vertical axes. And I was saying, like, for problem instance x1, we're going to use this parameter setting denoted psi of x1. For problem instance 2, we're going to use this parameter setting psi of x2. So how can we learn this kind of mapping from inputs to parameter settings that are good for that particular input? And another direction is to provide data-dependent bounds. So a strength of the results in this paper is that they are input distribution agnostic. So they apply to any distribution over problem instances, but they can be loose for non-worst case distributions. So can we provide guarantees that improve based on the niceness of the underlying distribution, perhaps using some kind of covering style analysis or some maybe Rademacher complexity analysis, which would allow us to get data-dependent bounds, whereas pseudo-dimension and BC dimension imply worst case bounds. So with that, I'll wrap up and take any questions. Thank you.
Thanks, Ellen. So we have some time for questions. Let's see. So there is a question asked by Ruma DC. So I'm just going to read it verbatim. If the tuning of parameters is automatic, how do domain experts ascertain with great degree of certainty that the performance of the result is optimal enough for them to work with?
Yeah. So I guess that's related to the first future direction I described, where if you want to provide provable guarantees on how good the parameter setting you come up with, that's still a direction with a lot of open questions. I think people have been happy with also like heuristic approaches that don't necessarily come with provable guarantees on the quality of the quality of kind of your parameter search. In terms of like how good is the parameter setting on average over my training set, people have been happy with heuristic approaches, to which our guarantees would also apply. But the question of like provably good parameter optimization is also a great question.
Great. Any other questions from attendees or panelists? All right, so let's thank the speakers again.